And I would like to welcome everybody here to the May 2024 Minnesota Astronomical Society meeting, and that's everybody in house and everybody online. So welcome to the chaos. I would like to introduce, you just turned me down. Did you?
Just
Okay.
didn't want the ringing noise.
Okay. I can talk softer too. Oop.
I think it's good.
There we go. Trying a new little clicker tonight. So I am your president, Trina Johnson, and in-house we have John Zimmich. Dave Faulkner is out, and these are part of your board. Matt and Ahmed is here, and Jessie is here too with her pink hair, which she's around. Which does bring us to the membership. So here we are, kind of a repeat on colors and stuff from last month. So all the people that were traveling for the eclipse now get to see Conrad's picture that he kind of took through the trees with his, was it the Lunt? Yep. And so we would like to welcome, oh, that's supposed to be 5. All of our new members. We have 17 new ones and 4 returning members. So thank you very much. Are there any new members in-house tonight? So that way we can say hello. All right. No. What about people online? If you can find your chat, say hi, and we're happy to have you, and come out and come see us. We have lots of programs that we're going to be going through. For events before next month's meeting, which we always talk about sometimes in the future here, we have sunrise and sunset, which is getting longer. I'm so sorry, everybody. But we also have the Eta Aquariids meteor shower, which is a picture of them on where they start from, and I found it online. It was a very pretty picture. So, and then we have a lot of conjunctions, moon occultations, a lot of Venus with superior conjunction. And then on June 6th, we are back here and online and with the new moon. So I'm not sure how many people will be at that meeting, but we'll be here. And if you miss it, it's always going to be recorded, and you can watch it on YouTube later. And then Antone is actually in the house, so I will welcome him to come up with the microphone and talk about our lovely LonerScope program. He is back. I love handing off microphones.
Yes, well, of course, we have our LonerScope program, a very popular program here in the club, a major draw for new members, I might add. I often get, I'm often the first contact new members have with the club. They say, oh, I can borrow a telescope. I'm going to sign up. And it's great. Anyway, yes, all members can borrow one of our telescopes. You just go online under the LonerScope program. You'll see all the list of telescopes that we have. We have Dobbs, we have refractors, we have a solar scope, some binoculars, lots of Schmidt-Cassegrains, and just make your request on the line. It comes to me, and then we make an arrangement to meet in my driveway, and I will let you use one of our telescopes for a month. We also have our collection of DVDs. There we go. These, I think the last time I was here, I said this. These are really underused. They're really very good, but all things astronomy. I also have those, and if you'd like to borrow one of those for a month or more, because they're pretty long, some of them, just let me know on the online form, and I'll take care of it.
And speaking of the online form, I actually have a little snippet of how to request that.
Oh, there we go. Yep.
From our homepage, if you go down to membership and select LonerScope program, you'll see a little bit of what Antone was talking about and your equipment request to fill in your name, email, phone number, and all the other stuff.
Yeah, and if it's a new member wondering what kind of telescope, if you'd also give me some information about your observing experience, or if you don't have any observing experience, that's fine too, and I can help set you up with a telescope that would be appropriate for you to use.
Awesome. And how many do we have now? 18, 20?
19. We have
19.
19 instruments all together.
Okay. Mark has a question.
Mark, we do not have an imaging setup.
Are you looking for an imaging setup, Mark?
Yeah.
Excellent.
Yeah. Yeah.
Yes, Cherry Grove has an imaging setup.
Yeah.
Oh, is okay. Well, here's a request out to everybody.
Mm.
If you're willing to donate an imaging setup, please contact Antone. We would love to, well, we would think about having one as part of the club.
We would have to think about it. I mean, most of our borrowers are less experienced users. And stepping into an imaging
Mhm.
rig as your first look through a telescope would be a challenge, I think.
Yeah. But before that, we have the training at CGO for the
Yep.
imaging equipment down there. And we also have ELO has imaging that they can have training on. So contact one of us or through the MAS board, we will find a person to get you in touch with to help you get trained
Yeah, so
in
it is-
imaging.
It is available.
Yes, yes. All right, thank you.
Mhm.
Just give that to Matt. We have a lot of star parties. This is so cool. So we have ELO has the public star party on May 11th and June 1st, because that's before our next meeting at 7 p.m. We also have Spring Astronomy Day. Doug, do you want to talk about that a little bit? Oh, okay.
What do you want to know? We have speakers lined up and we have prizes.
Okay. And
Starts at,
is it just the one day or is it all weekend?
no, it's one day.
Okay. All right.
1 o'clock will open for speakers at 1:30. Do you guys want to know who the speakers are?
No,
Okay.
we'll look at the website for that.
Prizes,
So,
7 o'clock.
okay. That sounds
Telescope
good.
giveaway, in case
Excellent.
anyone needs one. But it is the 18th, not the 19th.
19th. Huh. All right. I'm dyslexic on my numbers, so thank you so much for that correction.
Okay.
And then, excuse me, we have the BSIG observing session at Metcalf Field. Yep, hand it over to Suresh.
Friday, May 17th, we moved it up a day so that Spring Astronomy Day will be nice and free on the 18th. So we got rained out last week for the first one we tried at Metcalf Field. But we're hoping on the 17th, it'll be good weather and everybody come out. We need volunteers too, if you want to volunteer. So
Sounds
any
good.
questions, let me know.
Especially with that. Matt, do we know when the electrical power is going in? Do we have a date?
Okay. It is in progress.
Okay.
I believe the box is up and I think the run is still in progress.
Okay.
So I haven't, what? Yeah, the Biffy or whatever you call it is all serviced by now. So it's good to use the area if you need to.
Yep. Perfect. And if you have questions, just let us know. We'll help you out there. And then Cedar Creek is having is it their first public star party this weekend? All right. You want to talk a little about that, Mr. Mark Job? Yes, I think you need to. That's okay. I volunteer people for this.
It's the
This is what I
simple
do.
thing. We're having a star party at Cedar Creek. Wow. I didn't do anything, but that was kind of cool. Yeah, the star party starts at 7. I know it doesn't get, sun doesn't even set till after 8, but we'll have a presentation and since most of the people that show up there are mostly newbies and haven't even really looked through a telescope, we do a little bit of telescope 101, kind of show them around, show them the place. And it's always a good time, and weather holds, we're going to even have more fun than normal.
Mm-hmm. No rain, no clouds. Clear would be good.
Yes.
Yep. Look on their website, just look up Cedar Creek Conservation. Yeah. Yes. And then we have member offerings. So CGO is going to, hopefully weather permitting, hosting the Messier Marathon on May 11th that's a Saturday, with the backup being May 10th. And we should also be doing a little bit of training ahead of time. So stay tuned for that, because I know we only got partially done with the last one. So we have to do a little bit more finishing up with the training at CGO. And then LLCC open nights to register on the forum to reserve a bunkhouse spot, so you're not sleeping out in your car. Do you want to talk a little bit about that, Baltz?
Yeah, so LLCC is open. I'll look on the weekends on the calendar. There is a work party this weekend. Committee's going up there and maybe get lucky for a night or two. But we are installing internet up into the LLCC observatory and upgrading the equipment. So everything is looking good. So hopefully by NNSF, but by the way, NNSF registration is open. So if you look at the website for LLCC, there's a link to register for NNSF.
Excellent,
Yeah.
excellent. Which is the only time you can get training for up at Long Conservation Center. So make sure you sign up for that, because it's a 2-day event, sort of. It's 1 day, but there's also videos and things that you can watch ahead of time potentially to help on that one. But that's still, you can get trained on a 25-inch and a 30-inch Dobsonian. And you will definitely need that, because the carts are really cool to roll out, and yeah, it's a bit, but well worth it. And then speaking of the training, we have the ELO dates for key holder training. There was a note I had for training in July. I'm not sure. We'll double check on that one. JJCs, CGOs, and LLCCs. So stay tuned, and we'll have these posted with the happenings and on the forums. But mostly watch the forums for signing up for all of that under their respective discussion forums. And public service announcements. So this is an open forum. So I have Rebecca Messer please, if you wouldn't mind talking a little bit about new member orientation. And while we do that, if somebody lost a purple USB cord in the parking lot, I have it up here.
We're having a new member orientation May 25th, a Saturday, up at the Roseville Public Library from 10:30 to 12:30. So if you're able to come, learn some stuff, talk to some new members, that'd be great.
And
it's not on Zoom.
Nope, it is not on Zoom. You have to be in person. Rebecca, do we record each one, or is it?
There is yeah,
There is an
thank
old
you.
recording.
There is
for
an
it
old
out
one that's
on YouTube.
recorded. Yes. So you could get all the information go to this website and see when the training is and
Okay,
all that kind of stuff. So there is a version
that's out there.
that's out there.
Multiple times, but every single time it's scheduled, I'm out of town.
Oh, no. Change your weekend. Change your weekend. All right. And then I will have Ahmed come up and talk about our next meeting with his goofy little background that doesn't match any of my other slides.
I do my astrophotography when I'm doing my computer games. You can see my spaceship. If you're interested in space themed PC games, I can tell you a lot about them, and computers, you need to support them. So that's how I do my astrophotography. Anyhow, so like the 2017 eclipse and like the eclipse that happened in 2023, we're also going to be hosting club members' pictures in the June meeting. So send your pictures to programs@mnastro.org. You can also send a video, a time lapse, not only pictures of the eclipse, but if you've gone out there with a group of people, like I went out with John and Suresh and my sister and others and Phil, send pictures, of other club members, the people who are out there, their reactions, all that stuff. I'll include it all in the slide deck, and pretty much that's what our June meeting is going to be.
Mhm.
So any questions? Okay,
Sorry,
move on.
questions.
Sorry.
Nope.
Okay, let's keep moving.
Okay.
Okay, second thing is, we have refreshed our Facebook page. We have a Facebook coordinator now, and Chris Bethia. She's been doing an amazing job. Send us pictures. Send them to Chris. She'll post them. You know, if there is anything, send it, and we can actually post it to the Facebook page. And also, as members, interact with the page. If you like something, like it, you know, like the page itself, like the postings, and spread it to your friends and family. We want to get the word out there on social media.
One more.
And then last slide,
Yay.
we've also refreshed our merchandise store. So now you can actually go and buy, and we've consolidated the offering. We plan to actually have more colors for t-shirts and sweaters and all that stuff. We're working on it. And Jesse here is going to be helping us with some new designs, right? So thank you, Jesse.
Mhm.
But we're going to have more stuff, but we just reset the website. We just cleaned up the store, and pretty soon here there'll be more. So go out there, buy the club merchandise, and the club does get, actually, I don't know how much, but we do get something
We
out
get
of it.
something out of it.
So
Yep.
go ahead, you.
Reported a while back that the price that was listed next to an item was different from the price in the shopping cart when you went to buy it.
That's the old page.
Yeah. Yeah.
All that stuff is fixed. Yeah. And
Okay.
that's it. Any
That's it.
questions? Okay, thank you, Trina.
Thank you, Ahmed. All right. And then Astronomical League Awards. I don't have any from Terry, but I will tell you what it is about. So the Astronomical League is our parent company, and for each of our members, we give them $5 until July, and then it becomes $6 in July. That's when it goes up. And what they do is they, of course, with us, they provide a way to promote you to observe programs. Sorry, my brain's kind of fried right now. And it's really interesting, but Jerry does take care of that. And the immense things that you get out of that is you learn how to have patience, you learn how to see where your stars are. It's really interesting, but there's also some bling that you get along with it. So you can get certificates and pins. So if you see some lanyards around, we have the pins and the bling that goes along with that. Mark, do you want to share? But the parent company of Astronomical League also supplies you with the reflector magazines that you arrive in your mailbox. I believe it's every other month or every quarter. And it just shows everybody over the country that has completed observing lists. There's over 80 of them for you to do, from beginners to children, and then beginners, and then to advanced. It's a wide range. And if you're not sure what to look for, where to start, the Astronomical League Awards or observing lists is a place to start. So, I mean, the basic one I liked, which showed me a couple different constellations I didn't know, is a constellation hunter. So, you have to go find them, and a little bit of sketching, not too bad, but it's very well worth it. So if you have any questions about it, let me know. Otherwise, I think in 2 months, Jerry will be back, and he will have a nice overview for everybody that's out here and all the new members. So tune into that one, so you'll have a very in-depth view of what this program does. So like I said, I have no awards or pins to hang out, but his saying, which Jerry has coined, get out of there and observe. Okay, that was my little thing. We're on YouTube, just a little bit about that. So in case you're new, Rebecca will have a little bit more about this as far as on YouTube and what we have, where it goes and things like that. And if you have experiences, I'm pretty sure everybody here has an experience of an eclipse trip. Father Brown would love to have those articles. It doesn't have to be long. It doesn't have to be in depth. You can include a picture and say, hey, I went here, in a little paragraph about it. He will publish it. The Gemini is the only newsletter that is member-only articles. So we don't have any outside advertising. It is everybody that's here, and we like reading about it. It's very interesting. You all have very good stories. The deadline for the June published date is May 10th, and the next one is July 10th for the August published date, because that's every other month. And anything that doesn't go into that one, you can send to the happenings. Dave sends that out every Tuesday, like clockwork. He's very good at his stuff. And so any events that you have for the weekend, any little notices that you have going on, send him a little email and he will get it into the happenings, but you have to give it to him by Thursday. So that way he has time to prepare it over the weekend. And at this time, I will hand over the presentation to our Mr. John Zimmich, which I think we're still working on it, but it's member minutia to replace formerly Better Know a Constellation, because nobody wants to talk about the constellations, but we want you to talk about something else, space or astronomy related. So it's a wide range. Here we go. It just took a while to load.
If we need to, oh, look at that.
Ha.
Ta-da!
All right. You want a
Do you have
clicker?
does your clicker and the pointer work on there? too?
Yes.
Okay,
Here.
so there, that's what I'm talking about. And in the scientific visualization studio, the particular site I'm going to be referring to is the Moon Phase and Liberation site, and how to use it as an observing aid. I found it.
Is it liberation or libration?
Oh, excuse me, libration.
Okay.
I'm sorry.
Are we liberating the moon or
Well,
liberating
well,
the moon?
We can. I mean, so what this is when you go into the website, and I'll have a link to it on if you do NASA SVS rather, and it's going to bring you right here, and on the not here, but bring you to their site, and on the front page you'll also see moon phase libration, and then you can click on that. The opening page is going to look just like that. I don't know if I can move. I don't trust this, but the middle is the pointer.
Well,
Okay, then I won't do that. But so you've got when you go up to this page, it opens up with the current date time, and it'll have the phase of the moon, and then it'll give you an option to download. And what it does is you can download an image of exactly what you see on the screen for that date and time. So you can program in any other date and time, and that's of course how I really used it. And you can go back to about 2011, I think is when they started these. So 2011 all the way up to current. So why using NASA SVS? Why is that? Well, observing the moon, one thing is very critical, and that's monitoring the phases of the moon. And it's because we want to observe targets when they're ideal with lighting, because that's when we see them at their best. Well, this helps you because you can see, you put in a date and time, and it'll show you the moon, where the terminator is, and exactly what the object is you're looking for on the moon, what it's going to look like. And another reason is the moon is kind of tricky in its orbit. We can actually, the moon precesses, it's in an elliptical orbit, and there's perturbations. The sun is probably the most. The sun, in fact, influences the lunar orbit more than the Earth does. But so the moon, and you'll see this later on, and where I'm going to go with this, I was really surprised when I checked this out and how the moon's orbit works. And it's really amazing. I'll point that out. The positives of these variations is we can see 59% of the lunar surface. So we can actually see around the corners because the moon is wobbling up there and it's moving out in front of the Earth, and it's moving behind the Earth as far as its rotation. So we can see around those edges. The negative to that is if we're trying to observe things by either the poles or along the limb, they disappear. There are certain periods, and they can be lengthy, where these things just aren't visible. And if you're working on Lunar 2 observing program, there can just be times when, guess what? You don't just wait till the moon's lit up. Nope, you have to wait months to see that crater or mare or whatever. And the movement of the views that we did talk about is libration, and SVS helps with planning to observe to optimize those targets. Well, I'm working on Lunar 2 right now, and it just so happens to be that the observations I have left, I have to wake up at 3 in the morning to see these things. And I don't want to wake up at 3 in the morning and find out that, gee, guess what? Libration put the thing around the backside of the moon. So it's a beautiful, clear night. I'm out there at the scope and, okay, well, the moon looks nice. But yeah, so that's where it's going to help out. And this is an example. This is one regarding the Terminator and a shadow. And in the Lunar 2 program, one of the objects that we observe is Keys Pi, and it's a dome. Domes on the moon are really interesting, and they're very difficult to see because they're just little mounds. And if you look at the screen where my arrow is pointing, you can see the crater Keys. It looks like a hand mirror. And the little dome there is to the lower left of it. It's just looks like a little round circle. It's a little hump. That, if it's going to be clear, and I pull this up, May 18th, and it goes universal time, this is when you want to look at that. Okay. And you can see that's what you're going to be looking for. Now, if you wait 2 days, that's what it's going to look like. So you're going to have where the arrow is pointing, you're going to see just, this thing that looks kind of flat. You're going to be able to see barely Keys crater because the shadows aren't there. So that's just 2 days. So if it's cloudy on the 18th, you better hope for the 19th or maybe you think ahead and do the 17th, but then it might be in the shadow because, so these are the games, and this is where this thing really is nice because you can just put in your dates and see what's going on. Another thing, this is a Lunar 2 observing program. Now this is the libration effect. Mare marginis and Mare smithi are two of the mare that you have to observe. And you notice they're right by the limb there. Now we're already past February 15th. This year was very favorable with libration. That same night, May 18th, those things aren't visible because see where my arrows are pointing? They're around the backside of the moon up there. And you can just barely see Mare marginis at the top, maybe one of the little arms on it, little peninsula. Well, if you go out on June 10th, up there, you can see that they just come around the edge of the moon a little bit. If you don't observe it then, they're not in favorable libration until the end of the year, December. And they'll just sit, it'll be, when they're visible, as far as the surface of the moon that's pointing toward us, it's going to be in the shadow. And then as soon as the light hits it, they move back behind. So end of the year, early next year is when you'll have to catch this if you don't catch it in June. Oh. And then if you, oh yes.
So what you can see there, like those dates that you can see the Mare.
Yes.
That is from anywhere on the planet Earth, correct?
Correct. Yes, that's visible anywhere on the planet Earth. One thing nice about the moon, well, it's the same with a lot of the celestial objects, deep sky and everything. They're visible everywhere on the Earth. There's some very minor differences. The moon is close enough where you are on the Earth can influence. So if you're looking at something that's right barely on the edge, you probably don't really want to be observing it anyway, unless it's like a personal challenge. But but you can, it's mostly, these are visible anywhere on the earth. And then my next slide here, now if you would just happen to view an eclipse and take some pictures, and you happen to get one, this is a shot I got with Earthshine. And you probably let me turn lights down a little bit over here. But you can see, and you want to see how the moon is. If you're going to go back, you can see the image that I pulled up from SVS. It kind of matches. You can see, Mare Crisium is really obvious on the far right on what appears to be the equator. And then in the lower right corner of the SVS, I'll get into this little thing later, that display, you can see that's the position of the moon. So you can tell the way the pole is situated. And it's over there, about, I think it's 40 degrees. No. I think it might be 30, but well, let me see here. 5, 10, 15, 20 degrees. Okay. So the moon's tilted 20 degrees, the pole. So yeah, you can use it for stuff like that, just to see, yeah, guess what? My alignment was right on my scope because the moon lines up. But then this next part that I'm going to get into, this is really a fun, I spend hours on this. And I don't know if maybe I'm just nuts, but if you're like me, you just might. And they put this to music. What it is, it's the entire moon for 1 year, every hour is going to be this video sequence. And this thing is loaded with information. If we start in the lower left, I talked about that a little bit. That's the position of the moon. So you can tell by the equator if it's tilted back or down, up or down, back or toward us. You can tell where the pole's right or left. Then the line going across the middle is an in-scale drawing of the Earth to the moon. And it has, the moon is all the way over on the end. It's about at the far point. That's where it was on January 1st, 2024. It's at about its furthest point. And you can see that's about 32 Earth diameters. And the closest the moon gets is about 28 Earth diameters. What's interesting, the part that really amazed me is that I thought, okay, it's an elliptical orbit, it has apogee and perigee, and they're just pretty consistent. No, they're not. The moon doesn't always get as close as it did the month before, and it's significant. And the moon doesn't always get as far away as it was the month before. And I didn't realize that until I actually watched this. I knew that other variations. The one at the top will show the lunar orbit follows inside that blue trail. The light blue is when it's above the ecliptic. And the dark blue is when it's below the ecliptic. And the nodes, that's when eclipses could occur. The ascending node is to the upper right and the descending node is to the lower left. So that means ascending means it's below the ecliptic going to above, and vice versa for descending. And then we roll around back to the other corner and it has all the lunar data. How many days old, what, there's a whole bunch of data on there that you really have to kind of read into it to see if it makes sense. The bottom one's the one that makes the most sense to me, other than the date and time and what the day and the diameter of the moon and the distance. But then the moon itself, it's going to label craters along the terminator, and you're going to watch this thing change in size because the moon's going to get closer to the Earth and move away. So to monitor that, just kind of watch the edge of the moon at the north, bottom and top as this thing plays, and you'll see how those get closer because the moon's going to be getting bigger and smaller. And so yeah, let's let this thing roll, and hopefully there isn't latency for people online, and this thing will run. Oh, audio. You don't have audio? Okay. Sorry. You're going to have to do this online because this music is really good. These NASA guys, and they have this for a number of years. But just watch this, and it's just fascinating. You can concentrate on any part for a while. And that top one shows where the sun is. It has the vernal equinox off to the right there. Kind of, yeah, kind of combination. It's called gravity. Well, guess what? That gives you a reason when you get the link at the end. Unless, Trina, you know any good music? Okay, well, there you have it. I recommend you go out there and use this tool. I found it very useful, and you can when you download those images, when you take that shot for the date and time, and then what I do, I just go in and I edit it, I blow it up and I crop it to give me the part of the moon that I'm looking for. And then I typically use my laptop when I'm looking at the moon, because who cares? You want bright things around so you're not burning holes in the back of your head. And so I just use my laptop and I have those images on there, and the images that print out from here are good enough that, yeah, you can really navigate. The only issue that I don't really consider it a huge issue, but this is all naked eye. So naked eye binocular, these would work fine. I have a SCT, so north is up, but everything switches left and right. So when I pull it in and image it, I just flip it horizontally. And if you're using a newt, you just need to flip the other way. And so then obviously all the writing's going to be wacko, but it still gives you that idea. And for planning, it's excellent, because there's no moon book or anything that will give you this good of information. There's some good stuff out there, and people have been using them for years. But especially if you're doing that limb and Terminator stuff, where that stuff's critical, this is really a nice tool. Any questions?
I think Jerry might have one, but it's a really expensive book if you can't find it on sale. Ask him about it, but.
Any questions? None? Okay.
Let's see if there's any online. I don't know. Yep.
Just gonna say, I just happened to be looking at the Wikipedia article on the libration of the moon, and it has a movie like this showing them. So you want to look real quick at something.
Yes. Yeah.
Just to get an idea.
Right. Right. Yeah. It's fascinating how, and like I said, the biggest thing that I never actually saw it really spelled out real well was that elliptical orbit, how drastic it changes from the Apogee and the Pregi,
Perigee,
or Perigee.
perigee,
I'm
pregee.
having a problem with words today.
Have you been drinking already?
No.
Okay. And I don't know how to help you. Well, I
I
suppose I
wish
should have
I
had a, I should, suppose I should have had a moonshot instead of a sunshot. Well, that's all right. Well, thank you, John. I got it. All right, I just have a couple more slides. Here we go. We have, like I said, for next month is our meeting on June 6th. Hopefully I got that right. Where we are featuring all of our 2024 eclipse photos and eclipses, people, travels, you name it, send it in. And then we will, of course, be online and back here in person. So at this time, I will, I think I forgot a slide. I did. I forgot a slide. Hold one moment. I know, it's introducing our featured speaker tonight, and bear with me because this is, I don't know why I have it hidden. Yeah, either microphone or me. There we go.
Is it on? Okay. I am not an expert, but I was very fortunate March of last year to see the Northern Lights. I was in Eastern Iowa, central Eastern Iowa. It was strong enough that we were able to get amazing pictures. Today, I've seen notifications that it looks like we're getting some, maybe tonight or tomorrow. So I don't know if anybody's got the app is called Space Weather Live. So I'm gonna keep an eye on it. Hopefully that gave you enough time.
Thank you. Thank you. Okay, and then I just have one other note before I introduce our speaker is that and the NCRAL conference in Green Bay is this month on May 17th through 18th at the Neville Public Museum. Astronomical Society is hosting it. So there we go. So now I would like to introduce our featured speaker, Professor Anna Williams of Macalester College, and she's going to be talking to us about our galactic magnetic fields studies with radio telescopes. So welcome.
Okay, so thank you so much for having me. I'm thrilled to be here and learn more about the Minnesota Astronomical Society. I'm embarrassed I didn't know that it existed until I got the email, even though one of my high school physics teachers who taught me AP physics a while ago is here and a part of the society. So thank you, Rebecca, for getting me here. You're part of my journey here. She got me into a bunch of like STEM camps when I was young too, so that helped as well. Hi. Are you coming up too?
Yep, and we have a featured guest along with our guest.
We do. So this is Izzy. You're gonna be on the slide in just a second. Oh, wait a couple slides. All right, so I am a professor at Macalester College. This is my 6th year there. So excited. I grew up in Northfield, so I'm excited to be back in Minnesota and learning about the Twin Cities. Since it was always like a 45-minute trip to get up to do anything up here. And now it's just, 10-minute bike ride to get to a bunch of cool places. So let's get started. So a little bit more about who I am. I consider myself an extragalactic radio astronomer. So I use radio telescopes like the VLA, which I have up there in the middle, to look at galaxies outside of our own. So that is me standing on one of those dishes, these 25-meter dishes. They're gigantic. And we have 27 of those that we can combine the data that are all the signals that they receive simultaneously to study things in our own galaxy and beyond. So here I have NGC 6946, the fireworks galaxy. It's a galaxy that I have studied a lot. It was a part of my dissertation. And so using these radio telescopes, I am interested in measuring the strength and the structure of the magnetic fields in external galaxies. So what we see here in the color scale in the background is H alpha emission. So that's showing the ionized hydrogen where there's star formation happening. And then those line segments are showing the orientation of the magnetic fields. I'll talk more about that. I also am a mother to a fur baby, and as you met Izzy, almost 3-year-old, and I've played way too much Ultimate Frisbee in my life. So that's a little bit more about who I am. So my goals for this evening are to hopefully give you an appreciation for magnetic fields. There's this ongoing joke that is, not quite as common as it was when I began grad school, but at the end of a scientific talk for someone to raise their hands and to say, so what about magnetic fields? Because everyone tries to ignore them. They're complicated, they're hard to observe. The math is difficult, modeling them is difficult, but they are important and they are everywhere. So I hope that you get an appreciation of what these things are, maybe outside of your use on your refrigerators. So we'll talk about what they are, where they come from, and then look at them astrophysically. So why are astronomers, why am I interested in them? How do we measure them? And then, how do we know these things about them, besides they can stick junk mail onto our fridge. So I'll get into that. So what is a magnetic field? So most people are probably most familiar with them in this context, right? A compass, your refrigerator, toys, RIP buckyballs, since they are no longer safe to be used around small children. I'm very careful with them now, but they are sort of my fidget toy at my desk. But right, we're used to seeing magnets in this form in our daily lives. These examples are mostly permanent magnets, not necessarily the compass. We'll talk a little bit more about that. But these are intrinsic properties in the materials, in the metals themselves. So a magnetic field in more detail is, this invisible force field, right? We can measure it around a magnetic object, like a bar magnet, right? When we dump iron filings around a bar magnet, they are going to orient themselves around the magnetic fields because they have a magnetic dipole moment that wants to be in orientation with the magnetic fields produced by that bar magnet. But there are also electromagnets. Right, permanent magnets are what we usually think about using in our daily lives, but then electromagnets are also really important. So if you have a current, it will generate a magnetic field around it. So this type of magnetism is really important also in our daily lives, but it might not be as recognized as our bar magnets. So we can treat, Einstein's theory of special relativity tells us that we can think about electric fields and magnetic fields as the same, just depending on what your reference frame are. So it turns out if you have a changing magnetic field, like dropping a bar magnet through this copper tube, it's going to induce an electric current because it will create electric fields that cause the electrons in the conductive material to start to move. And as that electric field changes, it produces a magnetic field. So just by having moving charges, we can get magnetic fields produced. And so that's how that, you drop a magnet through a tube of conducting material, it doesn't drop like you would expect it to with gravity, because there's this magnetic field that's being generated by the current that's in that copper tube that acts as a force against gravity. So outside of, our refrigerators, trains, a lot of public transportation is moving into using electromagnets. Your headphones, right, have a little magnet in there, and then you have a current that basically makes that magnet move back and forth to create the sound waves that you hear. In order to capture wind energy, we basically have magnetic dynamo, where the wind moves these wind turbines that moves a magnet and generates a current that then we can use to, turn on our lights. So why are astronomers interested in magnetic fields? Hopefully I've convinced you that you're surrounded by them all the time. And hopefully I've convinced you that, currents are important. If we just take a census of our own galaxy, the Milky Way, the total mass of the Milky Way is about 4 times 10 to the 11 solar masses. So 4 times 10 to the 11 times the mass of the sun, which is 2 times 10 to 30 kilograms. So it's a lot of mass. And about 10% of the mass of our galaxy is in the form of gas. So mostly hydrogen and helium. Of that, 25% of that mass, or that gas by mass, is ionized. All right, that means we've got free electrons, charged, protons, positive protons, and positive nuclei moving around, and possible to create magnetic fields in our Milky Way. And this gas that is ionized fills up 50% of the space of our galaxy. So it's just permeating everywhere, right? Our galaxy is just filled with this ionized gas. And so this image that I'm showing here is, again, an image showing H-alpha emission, which is an electronic transition when an electron recombines with a proton to make neutral hydrogen. And as that electron goes down to lower energy states, orbital states, it will emit hydrogen, or H-alpha emission. And so we can trace where that ionized gas is in the galaxy. And so that's how we know that it fills up about 50% of the space. And then if we think about stars, they're 99.9% ionized, right? So we got a ton of charged particles that are going to be moving around, and thus are currents and can create magnetic fields. And if we take a step back, outside our own galaxy, this is just a small portion of the Hubble Deep Field, where we have thousands of galaxies in just a teeny tiny speck of the sky. And so each galaxy has its own set of 100 or so billion stars that are going to be ionized. Each one of those galaxies is also going to be mostly filled in volume with ionized gas. And so there are plenty of opportunities for magnetic fields to arise and thus affect the motion and evolution of these objects. All right. So I guess my tagline was on this slide too. So, right, there are a lot of opportunities for magnetic fields to be generated and thus affect the motion of matter. Right. So how do we study magnetic fields? Astronomers aren't as lucky as basically any other type of scientist, where they can, put some stuff in a beaker, mix it up, see what happens, right? We can't manipulate things in our laboratory. And as you all know, our main tool for studying space is the electromagnetic spectrum, right? Using light, electromagnetic waves that are generated from astrophysical objects, detecting them with our instruments, and then, using our theory to understand how that light and that energy that we're receiving is produced. So even though magnetic fields are invisible to us, we don't see them around a magnet, we can observe their effects on light and matter, and that's the way that we can detect magnetic fields. So the primary tools that astronomers have at their disposal for measuring magnetic fields are radio and the lower energy portion of the electromagnetic spectrum. So radio, sub-millimeter, microwave, infrared, those are our best options. Okay, so how do these magnetic fields produce electromagnetic radiation that we can observe? One of the main tools that I use is synchrotron emission. So if you have relativistically moving charged particles, so electrons that are moving at a fraction of the speed of light, when they interact with a magnetic field, they will feel a force, which is going to cause that electron to then gyrate around the magnetic field. As it is accelerated, because it's changing directions, it will emit radiation in the form of synchrotron emission. And so we can observe this synchrotron emission in a variety of different sources on a variety of different scales. So when there are supernova explosions, we get we get synchrotron emission as the blast wave of this enormous explosion accelerates materials. Those materials, or that medium, is interacting with the magnetic fields. Those electrons get accelerated. They feel then the magnetic fields, the force from the magnetic fields, and emit synchrotron radiation. On a larger scale, Jets produced by supermassive black holes will send ionized material far distances away from the host galaxy. That material will interact with the surrounding medium, circumgalactic medium, intergalactic medium, and interact with magnetic fields there and also produce synchrotron emission. So that's what I'm showing on the right here. We can also use polarized dust emission. So there are dust grains, and when astronomers talk about dust, we're not talking about like the dust bunnies that form underneath your furniture. Dust grains are basically as small and fine as cigarette smoke. So they're these very, very small particulates. But they will have a magnetic dipole moment associated with them. So if there's a magnetic field where they're located, they're going to want to line up with that magnetic field, just like the iron filings do when you dump them around a bar magnet. When that happens, light from, say, a star that then interacts with that dust grain is going to be absorbed, and that dust is going to re-radiate light. Basically, it's going to get heated from the star, and when it re-radiates that light, it's going to create polarized light because all of those dust grains are going to be aligned in the same way. So when they emit photons, those photons are also going to be oscillating in the same way. So basically, instead of having a bunch of randomly oriented electric fields, electric and magnetic fields, like you would get from, say, a star, after that light interacts with the dust grains, a portion of that light will be polarized. All of the electric fields will be oriented in the similar direction, and we can detect that. All right, you can detect that. Light, people buy polarized sunglasses for a reason. When light bounces off the road, it creates glare. You put polarized sunglasses on, it blocks that light. If we're wanting to detect it, right, we don't want to block it, but we want to, figure out which parts of the incoming light are polarized or not. And so that's what we can do. This primarily, this type of observation usually happens in the infrared. So it's not something that I use personally, but there are some really interesting results that do come out of these types of observations, such as observing star forming regions in the Milky Way. So here I'm showing an image of the Brick, which is a region that has it's a dark region relative to this massive region of star formation near the center of the Milky Way. And when we look at it in the infrared using Spitzer, we can see that there are magnetic fields aligned in this region that we can get from this effect of the polarized dust. So we can learn about the structure of the Milky Way's magnetic fields. On an even larger scale, I think this is one of the most beautiful images of the Milky Way that has come out in the past couple of years. This was created through collaboration with the European Space Agency and the Planck observations with the Planck telescope. But basically the color gradient here, the redder, browner it is, the more dust content you're seeing, the bluer, the less dust content. And then that sort of wavy pattern is showing the structure of the magnetic fields. So from these polarized dust observations, we can see that there are these loops of magnetic fields coming out of the plane of the galaxy. Along the plane of the galaxy, the magnetic fields tend to be aligned. And then out of the plane, as you move into the halo, there are these structures that extend away from the disk of the galaxy. The third measurement that we have is the Zeeman effect. So basically, if you have a very, very strong magnetic field, we've talked about these different transitions that electrons can do in an atom. If you have a strong magnetic field, that can create additional electronic transitions. So electrons have their own magnetic dipole moment. You put a really strong magnetic field around it, and it can enter different energy states. And so what I'm showing here is a small image. The orange black scale is an image of a sunspot. And so that black line that's going down vertically in the middle of it is basically where they took a spectrum. So just along that teeny tiny slit or that black line, they're only letting light from that region of the sun through. And then on the right in that green image, basically the Y position on the green corresponds to the Y position on the that sunspot. And then the X position is showing different wavelengths of light. right? So where there isn't a sunspot, you just get one dark line, which is just showing, that's an emission feature there, or, electronic transition there. And then once you hit the region where there's that strong magnetic field, that sunspot, we get the Zeeman splitting. So we see these additional electronic transitions within these atoms. So we can use the Zeeman effect with spectroscopy to study very strong magnetic fields. And this is, an important tool that we use for studying the sun as well. So I grabbed some images videos from the Solar Dynamics Observatory taken yesterday. If you haven't checked that out, I just love it because they, publish data basically as soon as they get it. For parts of the electromagnetic spectrum from the optical into the into the UV. But here, if I can get my clicker to go, right, we can see the sun rotating, and we can see, we're approaching solar maximum right now, so there's quite a few sunspots. Unfortunately, this is like a relatively boring part on the sun when we look in the, the optical continuum, what we would see with our eyes. But if we move into the UV, this is taken at the exact same time with just a different camera, right, at higher energies. And what we're able to see here are these beautiful magnetic loop structures coming out of the disk or out of the surface of the sun. I don't usually see that weird artifact. I don't know what happened with their processing there. But basically we can see that where there are these sunspots, there are these strong, bright UV emissions. Basically there's charged particles moving along those magnetic field lines, bumping into each other and creating this high energy emission that we can observe. Okay, and then here this is showing just the magnetic field structure. I meant to look up, I forget if black is, I think white is coming out and black is going back in, but basically showing that wherever we have a one of those loops, right, we've got basically a north pole and a south pole associated with those magnetic fields. Okay. And then the last method that we have at our disposal for studying magnetic fields is something called Faraday rotation, the Faraday rotation effect. So again, this depends on polarized light, and also it depends on using spectral information. So we want to disperse the incoming light, look at what's polarized, look at the polarization angle, and we can get a sense of the Faraday rotation. So what Faraday rotation is, basically if you have a source of polarized light or linear polarization, when that light is emitted and it passes through a magnetized medium, depending on the wavelength of that light, the polarization angle, so this, the angle of that electric field vector, will be rotated more if it is a lower frequency, longer wavelength than if it is a bluer, higher energy, higher frequency electromagnetic radiation. So basically, we can measure the change in that polarization angle as a function of wavelength to get an idea of the magnetic field along the line of sight. So I didn't put any equations in this talk, but basically the magnetic field along the line of sight times the density of your electrons times your path length determines how strong that Faraday rotation is going to be. So those are the three things that make up that, or that will cause that effect in the polarization angle. Right, so we just need to get a lot of information at different wavelengths to measure that change in the polarization angle. So all four of these different methods give us a different view of the magnetic fields. So synchrotron emission tells us about the magnetic field in the plane of the sky. So does polarized dust emission. Well, the Zeeman effect and Faraday rotation effect both tell us about the magnetic field along the line of sight. So with synchrotron emission, so I'm just going to focus on radio here, so synchrotron emission and Faraday rotation effect, I can use these two different observational techniques to come up with a three-dimensional picture of the magnetic fields in space, right? Because synchrotron's telling me about, the XY, what's going on in the XY plane. Well, that Faraday rotation is, the Z plane going to or from the source. So this is great. We can start to study three-dimensional structure for magnetic fields. All right, so what do magnetic fields do in space? The first thing that they do is they do stuff. I've said that they can affect things, right? First thing that they can do is deflect charged particles. So this is really important for us here on Earth. If the Earth didn't have a magnetic field, we would not have an atmosphere and we would not be here, right? So the magnetic fields in the Earth also create these beautiful aurora. I'm super jealous. I haven't gotten to see them. That's awesome. And so those magnetic fields redirect those high energy charged particles from the sun, send them down to the poles or just completely away from the Earth, and we get, the beautiful aurora. Magnetic fields in the galaxy, it turns out, also prevent us from detecting high energy charged particles from certain directions in space, right? There's these magnetic fields in the Milky Way, and any charged particle coming from some extragalactic source is going to feel a force from that magnetic field and be deflected. So if we want to understand where these very high energy particles are coming from, it's going to be really hard. We either have to know exactly what the magnetic field structure is in the Milky Way in order to model out their effects, or it's just going to be blind to us, right? So this weird spiderwebby image here is a simulation of basically showing that only charged particles coming from this region of space are detectable for us. Everything else is just going to be randomly oriented, and we're not going to have any idea, where those, coming from that direction, they could be from anything, right? From anywhere. If we could get them outside the Milky Way, that'd be great. But Voyager is just getting outside. Oh, yeah. Oh, actually, we can detect those here on Earth using when charged particles come into the Earth's atmosphere, they'll interact with the Earth's atmosphere and create particle showers and their own form of electromagnetic radiation that's unique. Right. So I totally blind. I should say we're blind in a particular direction, and being able to say that it came from this extragalactic source potentially. Turns out there's intergalactic magnetic fields, which also complicate us trying to figure out where high energy particles can come from.
Very well protected by something.
Yes, we are.
None of us can see.
Right, exactly, that we can't see. Yeah. So, but yeah, we're able to detect these things here on Earth actually using the Earth's atmosphere. It's a great tool. Yeah. Yeah, no. Yeah, I did. I was being a little facetious there. Yeah. If only. Right. All right. All right. So magnetic fields will deflect charged particles, and magnetic fields will also accelerate these charged particles. I mentioned before that, the electrons will feel force around the magnetic field and gyrate around them. They can also accelerate them. So supernova shocks actually end up creating these very strong, randomly oriented magnetic fields that charged particles will go back and forth across. And basically, it's sort of kind of think about it like a tennis player that's running, and then they hit a tennis ball, and then it comes back and they hit it again, but they're still running. So because they're running and hitting the tennis ball, it keeps getting more and more energy. So that's kind of what happens when these shock waves travel through, interact with the interstellar medium, and they can accelerate charged particles up to, 10% of the speed of light. So these happen when the supernova, so basically we have all of this material that's interacting with the interstellar medium. Novas are really just when we have reignition of fusion. Yeah. If there are novas that also have strong magnetic fields, if you've got a neutron star that has a very, very strong magnetic field, like a magnetar, that can, will accelerate particles, not in a detectable, not in a way that it will necessarily send cosmic rays out into the interstellar medium to the same scale or the same extent that a supernova explosion will. Yeah. Yeah, so actually something that I haven't included in these slides, but a new project that is just kind of beginning is studying a highly magnetized cataclysmic variable star, which basically there's, these two stars orbiting each other. and one of them is accreting material from the other, and it's very strongly magnetized. And so it does emit in polarization that we can detect the magnetic fields there. Doesn't necessarily have the same effect that these supernova, but they will, accelerate particles near those sources. Yeah.
Is that something that the supernova in the Crown constellation will do? Yeah.
Yeah, I mean, depending on the type of supernova, if there's a remnant left in there, then yeah, there could be something that, I mean, there will be likely be magnetic fields in that region.
Okay.
The highly magnetized remnants in that region will, they'll be dragging magnetic fields with them as they're rotating. And so there's a ton of interesting physics that happens there on top of the fact that it's just a very compact object that,
Cool.
yeah.
Yeah.
So this is the same, I should have mentioned before, this image is Tycho, thank you. I was just like, I had this. This is Tycho in the UV, and if we look at it in the radio, this is showing us the synchrotron emission. Yeah, I feel like if I have a brain gap on any sources in here, somebody's going to know what it is. Great. All right, so magnetic fields also confine particles, and this is what might happen with that nova, and similar to like what happens with the Earth's magnetic field. But basically, it turns out magnetic fields are really, really important for jet formation. So simulations were done to understand the supermassive black holes that were detected with the Event Horizon Telescope. And basically, in order to form these jet structures that can extend, multiple diameters worth of a galaxy outside of the galaxy, there must be relatively strong magnetic fields that are oriented such that material is going to be confined to traveling along that region where the magnetic field is, basically preventing material from exiting the magnetic field structure. And so this is important on large scales for supermassive black holes and galaxies. It's also important for star formation. We observe here this little video that's playing here is the protostellar disk. The protoplanetary disk, because there's a star that is formed here, a very young star. And so where it's dark, that's basically where the denser dust emission is. So it's not very sensitive at this infrared wavelength taken with the HST. But basically, there must be magnetic fields in these regions that are collimating these high energy particles and helping to get rid of the angular momentum and accrete material onto these objects. And then thinking about accretion and formation, magnetic fields can also provide pressure. Usually when we think about star formation, we need there to be cold gas that isn't hot enough to move around faster than gravity can pull it in. But magnetic fields can also exert a pressure. So if you have magnetic fields in a region, they don't want to get compacted. But because of the ionized state of the interstellar medium and also how diffuse it is, and relatively diffuse, the magnetic fields, we say, get frozen into the interstellar medium. So if you move a chunk of the interstellar medium, you're going to move a chunk of magnetic field. If you have a big chunk of interstellar medium that you compress into a small region, the magnetic fields that were in this region are also going to get compressed into that smaller region, and they're going to exert a pressure. They're not going to want to be, getting close to each other. And so it turns out this can have interesting effects in the masses of stars that can form in a given region, depending on whether or not that magnetic field can be dissipated and sort of relax its effect. Right, and we do see magnetic fields oriented in very interesting orientations relative to star formation. So here the red is showing you a jet from a protostellar region that has a material moving away from us, blue material moving towards us, and those yellow segments are showing the orientation of the magnetic field. And so we do see that these magnetic fields stay coherent and stay aligned during star formation. How they're oriented, though, is still an ongoing area of research to understand, what is happening in these systems. All right. So I have way too many slides. I think I'll just go over what we know about astrophysical objects and give some like teasers for things that I do. And then happy to continue answering questions that come up. All right, so what do we know about these astrophysical magnetic fields besides the things that I've already told you? And there's a delay right now that's showing up on my computer and probably to the people on Zoom, but not to the people in the room.
That's okay. We don't need to see it.
We very much do.
Well, you very much do. Are you very much?
I mean, I got more pictures of Aurora on here.
Oh, yeah. We definitely.
Oh, this is why I'm not on Zoom. It looks like I got disconnected.
Oh, no.
Doo-doo-doo.
Okay. Yep. Oh, well,
Maybe that's the end of my talk.
oh, no, we still have a half an hour.
Okay.
At least a good 20 minutes.
Okay. Yeah, I'm just like thinking about where I am in my talk, and I just have too many things. I was like, what can I tell them about magnetic fields? There's so many fun things.
When did you start? Other
Um,
than being influenced by Rebecca.
so I will say that I was most interested, or I read a Time magazine article that like got me interested in astronomy in like 7th or 8th grade, and then I think there was some NPR thing that came out when I was in college about like magnetic fields in the early universe and cosmic rays. I was like, what is this? And luckily the people that I ended up working with in grad school were also interested in those things. So
Cool.
yeah,
Excellent.
kind of fortuitous.
Yes.
Yeah. Okay, we're good? All right. So what do we know about astrophysical magnetic fields? We've talked about the Earth a little bit already. The Earth's magnetic field is produced by an electromagnet. So there we have this molten iron core that has a bunch of charged particles in it. And as it is moving around, as the Earth rotates, excuse me, and material is convected up and moving through the inner layers of the Earth, it generates this dipole magnetic field. And so this is the effect that we get with the aurora. This is how we have, been able to navigate for a very long time. And the strength of this magnetic field is about 0.5 Gauss. So here I will have G that stands for Gauss, which is the CGS unit for a magnetic field. For reference, your refrigerator magnets are 50 Gauss. 50, 50, right? So 2 orders of magnitude smaller for the Earth's magnetic field.
Oh, that's tiny.
Right. And then for the sun, on average, right, the sun has a dipole like the Earth. It's a little bit more interesting since the sun is mostly plasma, right? And as it is rotating, it mixes up that plasma along with the convection that's happening inside of it, moving these pockets of plasma around in the sun, moving magnetic fields, twisting them up. So this dipole ends up flipping every 11 years. So you've probably seen, maybe you've seen these butterfly diagrams before, but here blue is showing us magnetic fields going into the sun, yellow are magnetic fields coming out of the sun. And basically we can see that where, it's mostly blue and yellow here, and then after 11 years, we end up with yellow here and blue here. So during the solar cycle, these sunspots will form, at mid-latitudes that then kind of migrate towards the equator. And then once they reach the equator, that's when basically that big flip in the large structure of the sun's magnetic field will change. So it'll, north will be in the North Pole, south will be in the South Pole, and then it'll flip and the magnetic south will be in the North Pole and the magnetic north will be in the South Pole. Right, so on the order of about 1 Gauss for the sun's dipole magnetic field. Oh, I thought I had something in here. For the sunspots, those are closer to, as we can see here, tens of Gauss. They can get up to, several hundred or 1,000 Gauss. So the magnetic fields in those sunspots will be very, very compacted and strong. Then talking about those neutron stars, like the Crab pulsar here, we have a highly magnetized compact object that, the size of St. Paul, but the mass of the sun, right? Like it's over the Twin Cities, but the mass of the sun, compacted into this very, very small region. And the magnetic fields, then if you imagine the sun's magnetic fields with the sun size get shrunk down into the size of St. Paul, that one Gauss magnetic field is going to be several orders of magnitude larger. So the magnetic fields associated with neutron stars are about 10 to the 14 or 10 to the 15 Gauss. So, you know, many orders of magnitude larger than that of the sun. I should have put the time scale on here. Oh yeah, no, it's going very, very quickly, but I wish I knew the time scale associated with the images that were compiled here. But yeah, these are rotating, you know, many hundreds of times per second. Yeah. Thank you. Yeah. So here, right, this is these magnetic fields are affecting the surrounding interstellar medium and the you know, producing these shock waves as this object is rotating very, very rapidly.
We can send a speed of light problem to the thing that's propagating that far that fast.
Oh, yeah. Yeah. Well, I mean, we do observe things moving, jets moving that appear to move faster than the speed of light because it is Doppler shifted, and we do have projection effects that can be done to make things look like they're moving faster than the speed of light. But that, you know, speed of light is still is the speed limit for the universe, and it's, you know, great for, you know, for trying to understand the scale of things. If we measure variation in an object and we don't know quite how big that object is or how big, you know, the process is that's happening, and we measure the time variability, you know, takes light that long to get through that object or through that region, and that can give us a sense of how big that object is. And then if we take a step outside of our interstellar medium and our local environment and think about galaxies on a whole, as I mentioned before, galaxies have these beautiful spiral galaxies can have these beautiful spiral structures, magnetic spiral arms that can either be aligned with or in between the star-forming arms. If we look at the Milky Way in Faraday rotation, we see regions where the Milky Way's magnetic field is pointing towards us and away from us that we also believe are signs for a spiral structure in a large-scale spiral structure in the magnetic field of the Milky Way. And then when we look on edge-on galaxies, we see these really interesting X-shaped structures here. So the white contours are showing you where there is synchrotron emission. I believe this was at about 5 gigahertz or 4 to 5 gigahertz here. So the white contours are showing you where there is synchrotron emission, and those vectors are showing you the orientation of the magnetic field. So we see that there are magnetic fields that create these X-shaped structures coming out of the disks of the galaxies, which tell us that there are probably magnetic fields in the halos of galaxies as well. So when we look at the strengths of the magnetic fields in these systems, we have two different types of magnetic fields that we consider. Regular magnetic fields, which are just magnetic fields that are all oriented in a similar direction. So, you know, like our spiral arms or these X-shaped structures. These magnetic fields are a few microgauss, so 10 to the minus 6 Gauss. So these are very, very faint, and I just think it's incredible that we can detect them. Right? So these regular magnetic fields on the order of a few times 10 to the minus 6 Gauss will be coherent on the lengths of hundreds to thousands of light years. Then there's also this turbulent component that ends up having a lot more energy in it compared to the regular component. So the strength of the magnetic fields in the turbulent component is, you know, tens of microgauss, so 10 to the minus 5 Gauss instead of 10 to the minus 6. And here, those turbulent magnetic fields are aligned on the lengths of like hundreds of light years and smaller. So if you imagine all of those supernova events that are going off, injecting a bunch of energy, moving stuff around in very turbulent, violent ways, that's going to create this small structure, turbulent magnetic field. So again, I should have had the slide a little bit earlier, but your refrigerator magnets are 50 Gauss, MRIs operate at about 1,000 to 100,000 Gauss. And the Milky Way's magnetic fields are a few micro Gauss in strength. All right. And also just for perspective, I think I've remembered to put things in terms of light years and light minutes. But if I say parsec, it just means about 3¼ light years. So whatever parsec you see, multiply it by 3 and you'll get it about in light years. And as you all, I'm sure, are well aware, we are about 8 light minutes away from the sun. And so typical galaxies are, on the order of 100,000 light years in diameter. Okay. All right. So I should have had that slide, or like I said earlier, but that can kind of put into perspective here, again, what we're seeing in space relative to what we are used to interacting with here on Earth. And then if we look at even larger structures than these, what I think are really cool, beautiful spiral arm structures and magnetic fields, we also see these jet formations. So I mentioned this before. This is an elliptical galaxy M87, observed in the optical and infrared with HST, and we see this little interesting tail coming off of it, and that is a jet from a supermassive black hole. So this is an optical image from SDSS. It's showing a larger region of that galaxy, right? So we can see that there are stars that are, gravitationally bound to the system that extend out much further than what we saw in the previous HST image. So that little jet structure that we saw was teeny tiny. But then if we look at this region in the radio, we see all of this interesting jet structure coming out. So this little jet thing that we saw here is right here, and associated with, the material that is out in this region must have come out of, the previous little jet tail that was coming out of that supermassive black hole. So in these regions, right, we have magnetic fields that are strong enough and oriented and arranged such that material can get shot out in a coherent way out to, multiple hundreds of thousands of light years away from its position of origin. And so this is the famous first imaging of a black hole that was done with the Event Horizon Telescope. And so at that very, very central region, right, they've also looked at the polarized light from these radio observations, and they can see that there are magnetic fields that are aligned and oriented in this region. These magnetic fields aren't too strong compared to, what we see in neutron stars. They're on the order of 100 to 30 Gauss. I just want to make sure I had that. But for scale, XKCD put this great little image together for scale so that you can understand how big this shadow region is around this supermassive black hole. But basically, the Voyager, where the Voyager is located, if you drew a gigantic orbit at Voyager's location relative to the sun, that would all fit inside of that shadow region for the supermassive black hole. So that's like, the event horizon of this object approximately. And that's about, a day's worth of traveling at the speed of light to get to that. Just a little bit. I mean, closer than getting there, right? So again, this structure here that we observe is what is needed to create these magnetic fields. So somehow, I remember trying to read a laboratory plasma physics paper in grad school where they were trying to create little jets in the lab, and they were just having a really hard time because they would get these little kinks, and so they couldn't make them be stable and coherent for very long. So the fact that space does this naturally is just fascinating, and really, really interesting, I think. And we can model it now. These observations are helping to constrain our models. These observations are also really helping to constrain general relativity. And when we're trying to figure out how can we, make general relativity agree with quantum mechanics, these observations are great at, defining the parameter space and shrinking that parameter space, but they're also not helping us get much closer to getting those things to agree with each other.
Do they vary in strength or are they constant?
That's a great question. I don't know the exact answer to that. My guess is when I looked at the paper, they said it was about 1 to 30. So that's, I'm guessing, their error range in what their magnetic field strengths are as well. I wish I knew the answers to that, but I don't. One thing that might be, they might be limited by their sensitivity, right? Where we see that the emission is lower, we don't see the magnetic field striping in there, which probably means that the signal to noise was too low in the polarization for them to be able to show that. I'm sure they're making assumptions then when they're putting into models how uniform it is throughout that region, but I don't know for sure. Yeah. All right. So that's all that we know right now. I started to talk about things that we don't know, but there are, quite a few big questions about magnetic fields that we still don't have answers to. Like, how and when did the first magnetic fields form in the universe? We don't know. Were they just there after the Big Bang, or were they something that was created by different temperature and density variations that would create little currents and then little, magnetic fields? How do they grow to the strengths and the structure that we observe today, right? So how do magnetic field structures change as a function of redshift or change through different cosmic epochs of the universe? How do they affect astrophysical processes that then in turn define the evolution of galaxies? I mentioned before that magnetic fields can provide pressure support against gravitational collapse, and yet stars are forming. So what's happening to those magnetic fields? How are they getting dissipated to allow disk formation, planet formation, and star formation on the scales that we observe? And then beyond galaxies, we think there are magnetic fields in the intergalactic medium. What are their strengths? How did they get there? Are they sort of remnants from before galaxies started forming and collapsing? Or are they things that have been seeded into the intergalactic medium since the formations of stars and galaxies? We don't know. So this is where my research kind of steps in. So the idea for things that I like to study are to look at different points in cosmic time to try to measure the strength and the structure of magnetic fields so that hopefully we can fill in some information about, how strong was the magnetic field during the dark ages? How strong were magnetic fields as galaxies and planets were first developing? And so we have some ideas that, very early in the universe, maybe 10 to the minus 9, 10 to the minus 16 Gauss. Was this something, there are these things called the Biermann battery or the Weibull instability that could have induced those first magnetic fields when at a redshift of about 20. So, very shortly after the Big Bang. Then when we move further along in cosmic time, how did those 10 to the minus 16, 10 to the minus 9 Gauss get up to 10 to the minus 6, right? We need to go 10 orders of magnitude between what is created from a Biermann battery to the magnetic field strengths that we observe today. And then also, we don't know how long-lived magnetic structures are in galaxies, right? We observe these beautiful spiral structures in many galaxies. Sometimes, as we see here, they're aligned with the star-forming arms. And then with NGC 6946, we see that they're misaligned, right? They're in between the spiral arms. So is that a unique phenomenon that they're misaligned or that they're aligned? Like, what is the life scale associated with these large scale magnetic fields and the dynamo action that's producing these magnetic fields? Yeah.
So, fireworks galaxy.
Yep. I'm gonna grab water later. Yeah.
That's the fireworks galaxy.
Yep.
That's a starburst galaxy.
Yep.
It's been
I mean,
interacting with
it's
other galaxies.
more active star forming than the
Right.
Milky Way. Yeah.
Most of those come from interactions with other galaxies. This is why they get like that.
Mhm.
Could that be what's impacting the magnetic fields?
Certainly. Yeah, that's something that I had slides and I took some of those slides out, but galaxy interaction is very important for understanding the evolutions of galaxies and also, triggering star formation, like you said. And then those energetic events, right? That dynamo action is going to convert that, kinetic energy into magnetic energy that creates these magnetic fields. And so, in this example, right, we've got two interacting galaxies right now, or in this image here, as well. So yeah, certainly can play a role. I think there are more and more large-scale cosmological simulations that are starting to include magnetic fields. Their results aren't showing anything, like they're basically showing that magnetic fields probably aren't having a super strong effect in the larger dynamics that we observe. But in terms of how these structures are formed, that could be doing more simulations with multiple interacting galaxies. I don't know of those of simulations with that aren't these big cosmological ones. So like a smaller simulation would provide better details than the larger one. Yeah. All right. So let's take a closer look at NGC 6946. So this is located about 5.5 megaparsecs, right? So about 15 million light years away from us, 16 million light years. It is inclined at about 38 degrees. So we would say if it had an inclination of 90 degrees, it would be exactly edge on. 0 would be exactly face on. So it's, somewhere in between that. And then it's, it has a higher star formation rate than the Milky Way, but it's not like extravagant, right? So it's about 2.8 solar masses per year versus the Milky Way is about 1 solar mass per year. And then this is what it looks like in the radio at different wavelengths. So here we've got basically moving from shorter wavelength, higher energy electromagnetic radiation to longer wavelength, lower energy electromagnetic radiation. And so when we look at shorter wavelengths, we see, as I mentioned before, these really interesting spiral arms that are in between these star-forming regions. This grayscale is now showing infrared emission or where there is star formation. And so as you move from this shorter wavelength to longer wavelengths, one, there's some telescope effects, instrument effects of what your field of view is and how it's changing and your sensitivity. So, right, we end up detecting more polarized emission further out because we've got higher sensitivity with our radio telescope to larger scales versus with the shorter wavelength. But then this region where we see, some polarized spiral structure, it starts to disappear at these longer wavelengths. And so this was sort of perplexing. This was observed in a number of galaxies when they compared or when they looked at them at this 18 to 20 centimeter wavelengths that, where the galaxy was coming, whether the spiral arms were rotating towards us or away from us, it seemed like there was probably an orientation effect that was happening such that there was a combination of Faraday rotation and synchrotron emission and the magnetic field structure that was causing the light, that longer wavelength light, to be polarized. So then at shorter wavelengths, we can look further into the disk and further into the galaxy versus at longer wavelengths where basically the magnetic field structure is such that it causes the polarized emission to go away. It depolarizes the electromagnetic radiation. So at different wavelengths, it turns out we can look at different depths into the galaxy. So at the longer wavelengths, we think we're really only probing the halo. Maybe we're probing into what we call like the synchrotron thick disk that's above the star-forming disk. Whereas at the shortest wavelengths, 3 to 6, are we looking, all the way down to that star-forming disk. So this is basically a model of how that polarization changes as a function of wavelength due to these depolarization, Faraday depolarization effects. So basically, when we look at the shorter wavelengths, we're looking, at wavelengths around here. And so we get a lot of polarized emission. And as we move to the longer wavelengths, right, we end up getting depolarized. And depending on what that magnetic field structure is, we might see different amounts of polarization in between those two wavelength ranges. So where I came in was to try to observe at 13 centimeters, which is in between these two regions, to see, do we have this type of function to model that would best model our polarization, or would it, be one of these other ones? And so at 13 centimeters, we ended up recovering more polarized emission in this depolarized region, right? Where basically we could see all of the spiral arm, or nearly all of the spiral arm at 13 centimeters compared to at the 22 centimeters, but we weren't recovering all of it, right? We couldn't get this region closest to the center of the galaxy at 13 centimeters. So it definitely was bridging this gap between these two wavelengths in the radio, but there was still a significant amount of depolarization that was happening in that galaxy. Yep.
Question online.
Yeah.
Yeah, question online is just how do dark matter, dark energy interact with magnetic fields? Is it gravitational effects only, or?
Gravitational effects only, gravitational lensing. Because those things don't interact with any form of electromagnetic radiation beyond gravitational lensing and that type of effect. Yeah, we're not able to detect. Unfortunately, it'd be great if maybe magnetic fields were the key to understanding that, but no, unfortunately they're not. Yeah, good question. Any other questions?
Sure.
Okay.
Right now.
All right. Yeah. All right. So basically what I then did is I took all of these observations and I tried to fit a bunch of models to basically just different resolution elements across the galaxy to see what we would be able to get. And so we wanted to update our picture of NGC 6946. And so, right, we do have this idea that the broadband polarization probes different structures and Faraday depths. I already mentioned that. And because of the varying strength and the vertical, basically magnetic fields coming out of the plane of the disk, and toroidal, right? So that would be magnetic fields kind of going around this, like if you have a donut and it's going like from the inside of your donut around the edge back, not poloidal would be, around versus like going like this, toroidal, right? So the strength of the vertical and the toroidal magnetic field are likely varying with height. And the current model fitting that I did prefers basically inhomogeneous screens. So basically these are just regions of turbulent pockets of magnetic fields that have magnetic fields oriented a bunch of different directions. And there are a variety of scales of those little pockets of randomly oriented magnetic fields that then can lead to what we observe. So this is sort of an example of the data that I worked with to model. This is looking at that percent polarization as a function of wavelength. So that plot that we had before, but we fit it to the Stokes parameters. And these were, some examples of the screens. I don't really want to go into that, but what I think here is showing an example of a fit. And what I called this was, the not worst fits, right? Because we didn't have very good wavelength coverage. We did our best with the data that we had. We really tried to massage everything that we could get out of this data. But basically what we ended up seeing was that the models that remained tended to be these models that had multiple layers of different scales of magnetic fields. And so, yeah. Yeah. Yeah.
Would your models, I mean, we see it as a flat. Would the decreasing of it effect be because of 3D and it's moving away from us versus out?
Yeah, I mean, it definitely is that 3D effect of that depolarization that's happening. Motion, red shifting, or blue shifting isn't it's not moving on scales that would move it out of the electromagnetic spectrum. Because we've got, I should say that like, not with these observations, but with the VLA, we can observe from like 1 to 2 gigahertz and then like 2 to 4 gigahertz and 4 to 8 gigahertz. So that's, going from like 1 to a few centimeters and like a few to 10 centimeters, right? So we are observing a large portion simultaneously. So that'd be, yeah, it'd be great if you're like, oh, we just look at a different redshift. Yeah, right? Just slightly different orientation.
Yeah.
I should say that these models, right, as I said, the polarization angle is going to tell us something about how that polarized light was emitted. And then that depolarization, or how that percent polarization changes as a function of wavelength, tells us about that line of sight magnetic field. So these models are incorporating three-dimensional pictures of the magnetic fields that we're fitting to the data. Yeah. So basically, this is what I ended up updating the picture to look like, that in the halo of the Milky, or halo of the galaxy, there are these turbulent magnetic fields in addition to these larger scale vertical toroidal features as well. And they're on different scales than what we observe in the disk of the galaxy. And so those two different, which makes sense, right? We've got star formation that's happening in the disk, and like tons of like very energetic events that are happening. And it takes a while for that information and that energy to propagate to these larger scales. And so it's going to be on different scales. So we were actually able to, constrain some numbers for what those magnetic field strengths might be for in those different regions. And I didn't put numbers on here because I didn't think numbers would be super important right now. I can get that. They're on other slides if you're interested in them. All right.
We'll show that in the second time.
Yeah. And then I'll just highlight one other project that I've been doing that I'm currently working with students to try to update as well. But basically looking at the intergalactic or intra-group medium. So we know that galaxies interact. We know that they, merge and form larger galaxies. We also know that they will be gravitationally bound in groups. And those groups can merge to form clusters, and those clusters can form filaments of galaxies, right? And so we know that we've detected the signs of magnetic fields in the intra-cluster medium, but what about their, the building blocks for those clusters? Are there magnetic fields in between the galaxies in groups as well? So are there magnetic fields in the intra-group medium? So this is evidence. So here is the evidence for the magnetic field structure, or magnetic fields in the intra-cluster medium. So basically that Faraday rotation effect that I had talked about before, right? That we can measure the change in the polarization angle as a function of observed wavelength. And when we look towards the centers of clusters, we see larger variations or larger strengths of that Faraday rotation. And then as you look at lines of sight that are, further away from the center of those clusters, that strength of rotation measure decreases. So basically you have these sources of linear polarization behind the cluster. You measure the Faraday rotation, and the closer you are to the center, the stronger the Faraday rotation, which suggests that there are magnetic fields on the order of a few microgauss in the intracluster medium. So where did these magnetic fields come from? Were they something that was present in the groups that then made up the cluster? Was it something in the intergalactic medium, right, before the groups formed and formed the cluster? Were there instabilities during the cluster formation that caused magnetic fields to form? Or are galaxies we know galaxies get stripped of their gas as they move through a cluster. Can magnetic fields also get stripped with that and then end up getting stuck in the intracluster medium? So we looked at a loose group called NGC 2563. It's about 150 million light years away. It has 64 known member galaxies that are all within about 1 megaparsec, so about 3-4 million light years in sort of radius around it. Several of the galaxies have known hydrogen detection, so H1. So basically that means that we know that they could form stars, right? If there's neutral hydrogen available, that's basically fuel for star formation. So we know that, stars could be forming in some of these objects. And we liked this galaxy group because it also had X-ray observations. So we had an idea of the gas temperature and thus the gas density. So we know that there's hot gas in between the galaxies that's on the order I guess the hot gas has energies on the order of 1.2 kilo electron volts here. So I went after trying to map this loose group with the VLA at 2 to 4 gigahertz. So observations were taken in 2017 and 2020. The 2020 ones are the ones we're still working on with some students. So for scale, that's how big this field of the sky is that we're mapping with the VLA. And basically the goal of this project is to measure the rotation measure for lines of sight that are outside of the galaxy or galaxy group, and then lines of sight that go through the galaxy group. So the idea being that the rotation measure that we get from this other catalog is going to have rotation measure due to the Milky Way, the intergalactic medium, the host quasar, whatever is producing the linear polarization, and then some uncertainty. But then when we look through the galaxy group, we're going to have the Milky Way, we're going to have the galaxy group itself, and the intergalactic medium and the quasar itself. So basically we have a control sample and a target sample, and we want to compare our target with our control to see if there's a difference in the rotation measure to tell us something about magnetic fields in the intergroup medium. No statistical difference between those two samples, at least in the 2017 observations. So that was kind of a bummer, but it allowed us to say, put some maximum strengths on the magnetic fields, but okay, nothing there. But what was interesting was when we compared our sightline to members of the galaxy group, we did see a change in the rotation measure. So basically, the closer a sightline was to a known group member, the stronger the variation in the magnetic field, in the rotation measure, which suggested there's more variation or stronger magnetic fields in the intergalactic medium or intergroup medium close to group members. So this idea of there being magnetized gas that's being stripped out of galaxies could be what's happening. Or as those galaxies travel through the intergroup medium, they stir up the material, they compact the magnetic fields, and they increase the rotation measure that can be observed. So this has been seen in models. So this is basically a model of the intra-cluster medium. This was for a cluster where bluer is showing magnetic fields pointed away from the line of sight. Red is showing stronger magnetic fields pointing towards the line of towards the line of sight. I think I got this backwards. Sorry. Negative should be towards us. Red should be away from us. And so basically where there were group members, the gas got stirred up and compacted more in this simulation, which I think is what we're observing in this galaxy group, right? So either gas is getting stripped off of the galaxies and then magnetizing the intragroup medium, or it's getting amplified via compression and turbulence in basically the tidal wakes of these systems. All right. So for this study, we've looked at 184 total sources. 22 of them were polarized. Not all radio sources are polarized, unfortunately. It'd be great if they were, because I'd have so much more data to work with. But yeah, so we've basically got this part of the sky that some students are currently working on that I'm looking forward to filling in and hopefully strengthening these results, or not. We'll see. It depends. So these observations, how many here? How many pointings? There were 40 pointings, and each one of those pointings was about 30 minutes. So 20 hours for that study. For another study, I think we had upwards of 60 hours. So it depends on the project that we're doing. There are large proposals you can submit or small proposals. And, the one that I mentioned for the polar that we're going to go after this, magnetized cataclysmic variable. We're just going to try to look at it for 3 hours. Just one little thing for 3 hours to try to see its orbital period and how the radio varies as a function of that. So it can vary a lot depending on your science needs and then also what they're willing to allocate with your scientific arguments. Yeah. All right, I think that's all I was going to say about my science. Basically, trying to fill in some different parts of cosmic history. I didn't talk about this other study looking at intervening galaxies or looking for magnetic fields in intervening galaxies, but I've got a bunch more data to do some more things with that. So I guess I'll leave it there for now.
We'll
I've
have
talked
you,
for a
we'll
long
have you,
time.
we'll have you, it's wonderful. We'll have you come back though.
Okay.
Any chance for questions?
Yes, I can answer questions.
Bit of a question. Actually, I got 4 of them. Bit of a chicken and the egg question about the magnetic fields and the galaxy formation. Is there a bit of tug and play? Which is first? Which came second? And the other was wondering about the Parker Solar Probe. Has data from that affected your studies? And the third one is about that couple years ago, the black hole collision they detected with the gravity wave detectors. Has that been any effect of your research, please?
Yeah. Okay. So I'll do the last one first because that's freshest in my mind. We would love to get information about like polarization information about compact mergers detected via gravitational waves, but right now we're limited by how quickly we can get our telescopes pointed or how quickly we can identify optical other, counterparts in other parts of the electromagnetic spectrum. So, right, there's really only been one object that we've been able to look at across the entire electromagnetic spectrum. With the gravitational waves themselves, we don't get that information. So we need to be able to look at it in the radio and the optical and the UV and the infrared to try to get that information. So we'd love to get that. There's actually somebody at the University of Minnesota. I don't know if you've had Pat Kelly come talk about his turbo project, but that's basically his goal is to try to like get, something he's interested in doing is getting a notification from LIGO that says, hey, we've got a gravitational wave. It happened in this portion of the sky. And then he's going to have a telescope that can quickly map it to see if he can try to find an optical counterpart so that we could follow up and get more information. The Parker Solar Probe, for me personally, since I'm interested in larger scale magnetic fields, it hasn't affected my research at all, but it is, it's just fascinating to see the information that we can get about the sun. And actually, we can touch the sun a little bit, right? At least it's very outer atmosphere. Yeah. And now the first question, the chicken and the egg question. That is something that we would love to figure out, right? If there were magnetic fields in the basically the medium that formed galaxies, or was it an effect of like we had to form the first stars first, and then that gave us the hot plasma, and then those erupted and then injected magnetic fields? We don't know. So we think at least for, we can explain the galaxies that we have today with start to explain it with some of the magnetic field structures that we observed earlier in time, but to know if it was those first stars or, those instabilities before even galaxies were forming or during the formation of galaxies, we don't know quite yet.
Thank you.
Hi, this is a follow-up on my previous question.
Yes.
And you kind of touched upon it, but I just wanted to clarify a little bit. And when you're looking at magnetic fields on the galactic scale, and you're trying to understand how they're changing and why they're changing, you have all these interactions with other galaxies, and you've got some stuff going on inside the galaxy too, right?
Mm-hmm.
And you picked NGC 6946, which has had the most supernova found in the last 120 years of any galaxy.
Mm-hmm.
So I was wondering, are supernova a good, are they a big part of this puzzle? Because, you may have one that's a local phenomenon, but you get these galaxies that are very active.
Yeah.
You could have a lot of these supernova over, a galactic timescale.
Right.
So what would that, have you looked into supernova as a possible answer to some of these questions?
Yeah. So some of the things that we tried to look at with the data, at least in terms of supernova, I don't have a Faraday rotation map of the galaxy. Maybe I have one further in here somewhere. But basically, we look for bubble formation. So basically, if you have magnetic fields like in the disk and you have some, super bubble, like a super like burst of star formation, so you have multiple supernova going on, you would expect that to then cause material to get blown out of the disk. And then magnetic fields that are oriented like this are now going to be oriented like that. So you'd have like positive and negative effects on your rotation measure. We didn't see as many of those as we were expecting to. So we tried to look for those structures, basically large gradients, large change in the Faraday rotation measure, and compare it where there are locations of H1 bubbles, because those H1 bubbles are going to show us where the gas got blown out because we had these supernova events, and there wasn't as strong of a correlation as we were hoping there would be. So in terms of the large scale structure, there doesn't seem to be a strong correlation there. Small scale structure, the strengths of those turbulent magnetic fields, yes. How over time that gets converted to the larger fields, we don't know.
Any other questions in-house or online? Matt? Any others?
Thank you.
All right. Well, a lot of thank yous online. So thank you in-house
Thank
from
you for your
us
time. I
as
should
well.
have checked in again.
Perfect. I love that. Thank you. Fascinating.
I think so too.
We're
you.
all magnets. This is great.
I mean, that's how MRIs work.
Exactly, exactly. So as we conclude tonight, just as a reminder to incoming. Hi, sweetie. Incoming. Remember to send your eclipse photos to, what is it, programs@mnastro.org. And we will see them all next month at our eclipse meeting. So thank you very much. Everybody have a good night. And for those that are around, pizza luce afterwards, or we'll see you next month. Thank you.